Well, welcome back, ladies and gentlemen. I look forward to continuing this very interesting day. And I'll start by introducing our next speaker, Andy Woods, who I've known since he was an undergraduate. And indeed, he was a research student of mine. I was very lucky indeed. He went to Bristol after a few years, partly in my Institute of Theoretical Geophysics, and then came back to Cambridge to be the head of the BP Institute. I think it's important to say that the BP Institute was set up by Dan Mackenzie and Andrew Mackenzie, and that BP put in £23 million for the building and everything. And 3 years later, there was a report from the chief financial officer saying they'd already got their 23 million back because mainly Andy's very useful comments and help to BP. And of course, Anthony played a role in that as well. He was frequently in BP. He made lots of comments, as I said before, to help graduate students and postdocs. Was famous in seminars. I often used to sit next to him and he'd whisper in my ear or say more loudly, "What the hell is this guy talking about? Why doesn't he make it clear?" Well, I think I've said enough about Andy. He's written, just like Anthony, on a broad range of problems, was elected to the Royal Society a few years ago, contributed considerably to multiphase flow phenomena. And now, Anthony, it's over to you. No, sorry, Andy, it's over to you.
Oh, well, thank you very much, Herbert, for very, very kind introduction words there. Yeah, and thank you very much for this opportunity to speak and give opportunity for public thanks to Anthony for all his support of the BP Institute over the last 20 years. Anthony's been a regular attendee of virtually all the seminars at the BP Institute, as Herbert mentioned, and his presence has been characterized by, at almost every seminar, by offering very insightful questions, focusing on the fundamental science or the application or both, but also questions just to help the presenter improve the clarity and logic of the talk, as Herbert mentioned earlier on. And I think this has had a huge impact on the quality of the presentations at the BP Institute and also the quality of the work of all the students and the faculty in the Institute. And Anthony's been especially encouraging about many of the different areas of work we've been engaged in, particularly our work on geoflows and environmental flows. And I came across Anthony in a professional capacity working on the volcanic risk at the Yucca Mountain Nuclear Waste Facility, where Anthony was actually working as the chairman of the US Department of Energy review panel on this problem. And we had many interesting and lively discussions about the different nature of the volcanic risk. But as well as Anthony's enormous contributions in viscoelastic flows, he also has had a very substantial impact on two-phase and multi-phase flows, particularly with multi-phase flows in pipes. And there's a lovely annual Reviews of Fluid Mechanics article looking at ways of measuring multi-phase flows. And I thought I'd just draw up two papers from Anthony's, and these are perhaps less well-known papers, but there's a paper Anthony wrote with, I think, his student Fortescue on gas absorption in turbulent liquid, where he came up with a very elegant theory for absorption of gas in a turbulent flow, and presented at the end of the paper some data comparing the theory and the data. And there was a very sobering statement at the end that clearly the scatter precludes the drawing of firm conclusions. And I think this is a very sobering lesson for anybody running experiments and coming up with correlations. But I found another very important set of comments in the conclusions of a paper he wrote on progress and trends in rheology on turbulent gas liquid flows, where he put the exact modeling of turbulent two-phase flows, taking account of every interface, is not currently practical. He also put that fluid flow modeling should be tailored to suit the imposed flow geometry, the flow regime, and then most importantly, the issues of greatest interest in any particular context. And I think this really captures Anthony's very clear focus on both the fundamental science, but also the relevance and to the application. And also the clear statement of experimental verification of theory being essential. And so I wanted to just talk about 3 problems that I think capture some of this spirit of Anthony's work. 2 on particle-laden turbulent flows, and 1 on the key importance of boundary conditions in problems. So as many people will know, there's a big drive towards the energy transition, which will require all sorts of metals, particularly cobalt and copper for the batteries of electric cars. And a lot of, on the seabed in the Pacific Ocean, there are these polymetallic nodules shown in this picture here. And these are presently being mined by a number of companies, and they're developing operations to mine these and extract the cobalt. Of course, there's a potential huge environmental impact this will have, because the ships, there's 4 kilometers of water, and the ships scoop up these nodules, put them on the ship, and then a lot of particles of waste material is then deposited back in the ocean. And so there's some important questions about where both these waste particles go, the waste sediment, but also the water, which may dissolve different metals from that waste sediment. And so we've been doing some experiments to look at what happens to particle plumes in a stratified tank. So I've got a video here of a stratified tank of water, and we're going to release some particles at the top of this in a particle plume. And what we see is the particles come in and form a turbulent plume, but because it's mixing the low density fluid at the top of the tank, it intrudes at some level. And at that point, the fluid spreads out, but then the particles continue sedimenting from this, forming this essentially cylinder of fluid moving down. And there's some beautiful wave patterns of moving up the edge of this. But our main focus is on trying to understand the deposition of the particles, and also the fate of the water with dissolved contaminants, because there's obviously, it's a multi-phase flow with issues of separation. Well, if we look at a simple plume of salty water moving through a density stratified ambient, what we find is that if we start off with density with depth, and we have an ambient density shown by this black line, as the dense fluid sinks through the ambient, it entrains a lot of the low density ambient fluid, and the density of the plume evolves, and eventually it reaches a point where it has the same density as the ambient because of mixing. There's a small overshoot because of the momentum, but then it bobs back up to this neutral density height. Well, with a particle plume, the situation is somewhat different. It starts off in the same way, moving down and training the ambient fluid, and overshoots. But at the point where it overshoots, particles then begin to separate from the fluid. And as they do so, the density decreases. And because the density decreases, the neutral height, or the neutral buoyancy height of this plume fluid, is quite a lot higher in the water column. And this just shows the result of an experiment where we supply fluid plus particles at the top, and we dye the fluid red. And we've left the intrusion from the pure salt plume in the tank. And what you see is that initially it goes to the same level, but then the fluid rises up and intrudes higher in the tank, and the particles then start to sediment out, forming this cylinder. And if we appeal to classic theory of turbulent plumes, we know that the volume flux in a turbulent plume increases with height to the power of 5/3 and the buoyancy flux to the 1/3. This is the classic work of Morton, G.I. Taylor and Stuart Turner. And so if we have a stratified ambient with the buoyancy increasing linearly with depth, we can work out the total amount of buoyancy entrained in the plume just by integrating over the depth of the plume the rate of change of the volume flux times the buoyancy entrained at that depth. And doing this, we end up with this expression. And if we divide this by the actual volume flux, we end up with an expression for the buoyancy of the fluid we've entrained. And of course, that's the fluid that arrives at the bottom of the plume when the particles start separating. And that buoyancy, if we look at the relation or conversion to a height, shows you that the intrusion will intrude at 5/8 of the height of the plume. And when we compare experimental data with this prediction, what we find is this is the top height of the plume, and this is the height of the intrusion. And there is some scatter here, so I'm nervous given Anthony's cautiousness about experimental data, but I think the experiments do seem to be consistent with this simple prediction. And what we see is for these small fall speeds of particles, the intrusion height's independent of the speed of the particles. Once we have much bigger particles, the situation is quite different, I would add. So the other issue we're interested in is the actual zone on the seabed where these particles may sediment from this cylinder. And if we do some analysis of the sedimenting material, we see it sinks through the water column. So this is a time series of this line. It sinks through the water column at a speed given by the fall speed of particles. And so if we match an area pi r squared times the fall speed times the concentration with the source flux of particles, and just use the dilution in the plume to get that final concentration, we can predict this radius. And it again agrees quite well with the scaling. So we're now able to predict the area of deposition. Well, the second problem I wanted to mention was about airborne aerosols, and particularly with the COVID crisis. The aerosols smaller than 5 microns tend to remain in suspension in the air for over thousands of seconds. And so if we're in a hospital context or other building context where people walk up and down the corridors, one of the key questions is, what is the residence time of the aerosols, and what's the impact of people walking along corridors in terms of stirring them up, because the weight people produce is very significant. And we've done some experiments at the Papworth Hospital in Cambridge where we've released clouds of carbon dioxide as a proxy for these small aerosols. And we find that with sensors 5 meters apart, that with no walking, we find the CO2 concentration rises when we inject a pulse, and then it decays over a timescale of 500 seconds or so, and spreads 10 meters or so. But with walking along the corridor, shown by the red lines, we find the residence time is much longer, and it more than doubles because of the mixing by the wake. And so to study this in more detail, we've carried out some experiments in a tank where we just move a cylinder back and forth in a tank, and we have some dye in the center of the tank. And this is false color, but it's essentially showing the way this dye is mixed up by the wake of a cylinder. And this is a high Reynolds number cylinder, so it's analogous to the wake of a person moving. And we hypothesized that the multiple wakes moving through this cloud produce an effective dispersive mixing. And so if that's the case, we'd expect the depth average concentration to evolve according to a diffusion equation. And the diffusion coefficient we found by some calibration of our experiments depends on the frequency, the radius of the cylinder, and the width of the channel or the corridor. And again, being nervous about Anthony's concern over good agreement of theory and experiment, here's a comparison of our model and our measured data. So I think there is something to commend this as at least as an approximate model for the way in which multiple people wakes mix up material. And this is just showing the Gaussian profile we'd expect at early stage after a cloud of aerosols has been spread as a result of this mixing. And the data seem to collapse nicely to this Gaussian over time. And so what we've done is we've taken this, and we're interested in really understanding what happens if an infected person walks along a corridor and breathes out a series of clouds of aerosol, which then may be mixed up both by a ventilation flow down the corridor, but also by people walking down the corridor. So we've carried out an experiment, and the top picture shows the photographs of the gray particles suspended in the channel with the cylinder moving back and forth to model people. And this is a false color just to help see how the mixing is occurring. And there's a net ventilation flow going from the left to the right, which is trying to flush the fluid through this system, as you'd imagine in the ventilation in a corridor. But while this cylinder moves back and forth, you can see it continuously back mixes and leads to a much longer residence time of the aerosol. And this is just a time series, this picture here, just showing how the color changes from red, which is the contaminated fluid, to the blue, which is the clear fluid, and the mixing is this zone in the center. And so if we normalize the data from this false color so that there's a vertical line showing the position of that front, we can see the mixing produced by this motion of people back and forth in spreading out the contaminant. And so we'd expect this aerosol the depth average aerosol to spread out with an advection or diffusion from the wake, but also a settling term from the sedimentation of particles to the base of the tank. And this early on, the way this front will move will be according to an error function with an exponential decay from the settling. And if we collapse all our experimental data at different times, over a number of experiments, and again, it seems to collapse. And so there's quite a simple way to try to estimate the spreading and the residence time of airborne aerosols and corridors, which leads to times of many tens of minutes and many tens of meters dispersion. And so this is an important factor in terms of figuring out safe distancing and occupancy levels in buildings, but also how you operate ventilation systems. But the third problem I just wanted to finish with was a problem about boundary conditions. And Anthony is always very interested and concerned in talks about boundary conditions and their impact on a problem. And one classic problem concerns the role of heterogeneity in permeable rocks and the impact this has on the flow, and particularly on the way traces are spread in the flow. So here's a photograph from a sedimentary layer with a little lens of different permeability in the center of the channel. And when we have a whole series of random lenses in a very laterally extensive porous layer, there's a lot of classic theory that suggests it's going to lead to Fickean dispersion. And but real rocks are obviously, they are laterally extensive, but they're vertically bounded, and particularly reservoir rocks have no flow through the upper or lower boundaries, because then they wouldn't be very good reservoirs if they leaked out all the fluid. So we can look at the impact of this. So here's a little experiment with a lens of high permeability, and we see that tracer moving along is diverted into the lens and moves out much more quickly. This is high permeability. And so after passing the lens, we've actually distorted the pattern of our tracer flow. And of course, if there's a whole series of these lenses in a row, this is a numerical simulation, then this trace is going to be spread out. And because the lenses may be at different heights, we're going to expect this to spread out and cause a Fickean type dispersion. But when we look at the variance of this, what we find is that early time, we do find this Fickean dispersion, the square root spreading of the variance. But at later times, the spreading becomes linear in time. And so we wanted to have a look at this. Well, a very simple model to look at this is to have just a very thin lens high permeability channel and look at the distortion or the diversion of streamlines upstream into the channel and then back out again. And what we find is there's a fraction of streamlines are diverted into the channel and then they come out again. And the probability of diversion into the high perm lens depends on where you are in the channel. So near the boundaries, there's less likelihood of being diverted. But in the center of the channel, there's a higher probability of being diverted. So you can look at the probability of diversion as a function of height in the channel. And what this leads to is a mean travel time. If you have many of these lenses, there's a mean travel time which is different at each height, and there's a variance of the travel time which is different at each height. And we can, from this, we can also work out that from this probability, we can work out the probability that a streamline is diverted into a lens or M lenses after passing through a section of rock with N lenses in it. And of course, the limit of this and the limit of a very large number of lenses is a Gaussian distribution. And we're going to have a mean flow at each height given in terms of the inverse travel time, and we can get a mean dispersion in terms of the variance. And so using that model, we'd expect that the distribution of concentration at each height in the channel follows an advection diffusion equation, but the speed in this advection is going to vary with position across the channel because the probability of diversion into a high permeability lens is greater in the middle than at the edges. And the diffusivity also varies with position. And so if we release some tracer and we watch it spread down the channel, what we find is initially it's spreading and controlled by the diffusivity or the dispersivity, but eventually this difference in the velocity profile, the shear across the channel, begins to dominate, and we find that the tracer spreads out in this pattern here. And so if we work out the dispersion in this simple model, we find, again, the Fickean dispersion at early time and then this linear dispersion at later times. And I think this just illustrates the key role of the top and bottom boundary, because without these top and bottom boundaries, we just have a pure Fickean dispersion. So really to draw to a conclusion, I just wanted to announce that at the VP Institute, we've decided to set up the Anthony Pearson Thesis Prize. And this is going to be an annual prize we'll award for the best PhD produced at the Institute each year. And there'll be a lecture given by the prize winner. We're going to start this in December 2020. And I think the conclusions of my talk are really captured by what Anthony wrote at the end of his paper about really the third point: fluid modeling should be tailored to suit the imposed flow geometry, flow regime, and most importantly, the issues of greatest interest in any particular context. And experimental verification is essential. So I'd like to finish there and thank Anthony again for all his support and wish him a very happy 90th birthday.
Well, Andy, that was terrific. If I may say, thank you for your turbulent and unsteady talk. Very enjoyable. I'm going to ask the first question, if I may, which is your work on individuals in corridors is, of course, very important and interesting. But what about trucks going down streets? And what's the effect of high rises on either side of the street? So the truck is, the air is confined. What does that do?
That's a very interesting question. So I think that has quite a lot of analogy with the issue of people moving up and down corridors. And in cityscapes, you get a lot of wind being channeled down the street corridors as it goes through a city. So I think that can cause quite a lot of extra mixing and dispersion. So I haven't studied that in detail, but I think there's a lot of parallels there with some of the.
Well, I think it is very important, and I'm speaking particularly as an Australian, because as you may know, the real problem in Australia with COVID-19 has been in Melbourne, where there are quite a large number of high-rise buildings that are close together. And I've often wondered what effect trucks and motion, and should trucks not be allowed to go in those regions where there's already a high quantity of COVID-19. But Melbourne's a little far away at the moment. So why don't we move on to allow other people to ask questions? Is there anyone who would like to raise a point? Oh, Jörg Imberger. Jörg, do you want to? Should be able to speak. Jörg, do you want to say something? Yeah, there you go.
Can you hear me?
Yes.
Andy, nice talk. Have you
could you speak a bit louder, Jörg?
Can you hear me?
Yes. Yeah.
Andy, have you thought of getting together with Thorsten Sturzer at UCL? He's doing numerical simulations of exactly the same problems that you're dealing with. High resolution and the way the virus spreads. Have you thought of getting together with him? Some very nice work being done of people getting on buses.
I'd very much grateful if you could send me his details. There's a number of us working on these sorts of problems and a number of different building types. So we much welcome sharing this work with everybody. The
second question was for the first speaker, Paul. In Canada, they had a virus, something that was contaminated 20 years ago, and every toilet you go to has strict instructions how to wash your hands. And they say 2 minutes is the minimum, and they tell you exactly what to do. Has he compared his theoretical ideas with any of that logic? And then my last question is, you guys, the talks are fantastic, what you've given. The English culture is really still alive, it looks like, in Cambridge. And it's a pleasure to listen to all you guys talk. Have you thought about the threat from Brexit, from social media, and from the way parents are giving up their job?
I think we need many, many hours just to answer those two questions. And Brexit, yes. Peter or Andy, do you want to say anything? Oh, Paul, sorry.
Well, I think the little calculations tend to indicate it's quite difficult to get particles off surfaces, and it's all to do with low Reynolds number flow, no slip boundary conditions. So I think the numbers are beginning to come out in the right ballpark. 20 seconds is not too long to spend trying to displace things, but the modeling's so crude that I really only believe in the qualitative aspects of what it says. But it's provocative and should stimulate further work, I think. And I'm not going to talk about Brexit. Thank you.
Oh, you started your talk by saying, "Oh, I didn't have anything to do during lockdown, so I did this." I mean, this is magnificent work, fantastic work. So the intellectual activity is very much alive.
Well, I think we need to move on a little bit. You clearly do raise some important questions, Jörg. Well, there has to be some work to be done in the future. And it would be good if the governments understood a little bit of fluid mechanics and the importance of it. Oh, Andy Woods says yes, very firmly correct.